In the last section, we've dealt with motion that's non-horizontal. Today, we actually move into a couple of different ideas. One is that, first of all, I want to take you in more advanced ideas where you have both acceleration in the x and the y direction. Up to this point, we've only had acceleration due to gravity in the y direction. Take a look at this particular problem. I consider this an advanced 2D problem. A forklift shown has an initial velocity of 2 meters per second and is accelerating at 1 meter per second, all to the right. So what we've got is this is already moving this way at 2 meters per second. That's its initial velocity. And it's accelerating in this direction at 1 meter per second as well. 1 meter per second squared. In addition to that, we have the crate. The crate is also accelerating. It starts out at a height of 4 meters, and it's accelerating downward also at 1 meter per second squared. So in this case, we have accelerations in both directions. And so the question, first of all, if the origin is set at the initial position of the crate, think about this as our projectile, what are the x and y equations for our crate's motion? Well, in this case, it's accelerating in both directions, and we're trying to figure out displacement. So we're going to use this equation that's up here on top, and we're going to deal with it. And up to this point, we've always had the horizontal as having no acceleration, but in this case, we're also accelerating horizontally. So what is it going to look like? Starting with that equation, the x position, the initial velocity is going to be 2 meters per second, and the acceleration in the horizontal direction is 1. So our equation becomes simply that. How about the y direction? Well, the y direction, any given instant, using that as the origin, the initial velocity in the y direction is 0, and it's accelerating downward at 1 meter per second, so using -1. And so we simply end up with this equation for its y position at any given time. So these two equations describe the x and y coordinates, with this as the origin, of the crate at any single point. B, at what time will the crate reach the floor? Well, when it reaches the floor, remember it started out at 4 meters above the floor, we just need to figure out, hey, when is this y position going to be 4 meters below where it started? So if we use those equations, use that equation, plug in -4, you can very quickly work it out. T is going to be the square root of 8, or 2.83 seconds. And so the question is, how far will the forklift move horizontally during this time? Our delta x. But this is the delta x in the horizontal direction. So using the x equation this time, we want to figure out what is the x position at 2.83 seconds. So just plugging in our time, we can get our answer. So it will have moved roughly 10 meters during the time in which it takes the crate to fall. What's different between this and projectile motion? Well, in particular, we have acceleration now both in the x direction and in the y direction. And so both of our equations have the 1/2 at squared term in them. All right. So range of projectile. Range is how far away it lands from where it started. So the range of this red projectile would be this distance right here. The range of this green projectile would be this distance right here, from here to where it lands. And the blue projectile, even further. This is used a lot. For example, when you want to try to kick a field goal, you try to get maximum range, typically on this, or if you're punting a ball, or even in soccer, you're trying to get it down the field. We can use our equations here, and again, we're going to make this point right here our origin. And the question is what do we know about this? Well, we don't know where it's going to be, but we do know the y position here has to be 0, because it's back down to where it started. So we can figure out what time y is equal to 0 again. If we do that, watch what happens. So using this equation right here, and this time setting y equals to 0, you can actually factor out a t, and then either t is equal to 0, which is true, at t equals 0 it is y equals 0, but the other term is the one that's more interesting, when this time is true. And we can rewrite it, well, we'll leave it that way for a moment. Leave it that way, and now we can actually figure out what the x position is at that time. How? We can plug in this time that we just found, sorry, it's really ugly, into time in this equation here, and we get this. And I put this in red here just to sort of signify it. It looks ugly, and it is in some ways. Here it's a little bit cleaner. But there's something interesting going on here. If you remember, and let me rewrite this just a little bit, you have a double angle theorem which has sine theta times cosine theta. And I know it's probably been forever since you've done the double angle theorems, but I'm hoping you kind of remember this, that there's one of them where 2 sine theta cosine theta is equal to some double angle theorem. And if you've forgotten it already, it turns out the sine of 2 theta is equal to 2 times the sine of theta times the cosine of theta. And so, why did I multiply by 2 over 2? Just so I can make this term equal that. When I do that, I can actually simplify it down to this. The range, that is the x position when y is equal to 0 again, is simply given by this equation, where v0 is your initial velocity, you square it, times 2 times whatever the launch angle is. So if the launch angle was 10 degrees, if theta was 10, you would do the sine of 20 degrees, divided by the acceleration of gravity. And again, what this is going to give us is how far away it's going to land. Notice that it increases dramatically with launch velocity. Doubling the launch velocity actually gives you 4 times the range. So one quick warning on this one, this only works for level ground. In other words, it will not give you the correct range if you're launching off the top of a cliff. Why? It would give you the distance to here, but that's not where this thing's going to land. It's going to land somewhere over here, and the range would actually be this distance. Nor will it work if you're launching up into some sort of a area up here. When you launch it here, it's going to end up landing earlier than the range equation would give you. So this only works for level ground. So this is our caveat. You can't use it everywhere. Some interesting things about range, just real quick. This is not a big idea, by the way. Range is not, don't think about it too hard. Notice something here. 15 and 75 degrees have the same range. Likewise, 30 and 60 have the same exact range. And 45 has the maximum range. You might say, why does 45 have the maximum range? Well, think about it. 2 times 45 degrees gives you 90 degrees. Sine of 90 is 1. That's the largest the sine can become. And that's going to give you the maximum range. So typically we think 45 degrees is maximum. The other big idea here is that complementary angles will give you the same range. They only give a few of them here, but for example, you could use 24 degrees and 66 degrees would have the same range. Why? They're complementary angles. They add up to 90. There's supposed to be an animation here. I don't think it's working. So for projectile motion, the trick to getting maximum range is to keep the object off the ground for as long as possible while we're maintaining horizontal velocity. And you try to go, you could go longer by going to higher position, raising your starting point. You can actually try that in your programming assignment tonight, or last night. But take a look at this real quick. And both projectiles have the same launching speed. The initial velocity vector has a greater vertical component in the second one. It produces a higher path, but the horizontal component's less, so the range is less. So take a quick look. I'm going to ask a different question this time. What's the maximum height of these projectiles? So take a look at this, and let's do some number crunching real quick. The first trick on this is, what do we know is true about this position right here? Well, that's when the vertical velocity, that would be v sub y, is equal to 0. And so we can figure out what time that occurs. So we stick in 0 for v sub y. Initial velocity was 50, sine of 45 minus 10 t squared. T. Solving it, you'll discover it's going to be at its highest point at t equals 3.54 seconds, just solving that equation. That still doesn't give us the maximum height. We want to know how far above the ground it's going to be at this instant. Well, you might say, well, wait a second, how do we figure that out? Well, remember, we always make this launch position 0, 0. All we really need to figure out to get maximum height is figure out what the y position is at this instant, because we know that's the maximum height. We can use the y equation back from projectile motion. I should put up on the screen, up on the thing here real quick. And if you plug in the time we solved, you'll get the maximum height. You can do the same thing with the other one over here. You can figure out the time and everything else. Sorry, this was supposed to show up first. Here's our x and y position equations. Here's our x and y velocity equations. Don't get those confused. This gives us the x and y components of velocity at any given time. This is the x and y position at any given time. Take a quick look at this one. Here's a quick brain check. What's the minimum speed a car would need to jump over a canyon that's 30 meters across? What angle should you make with the horizontal? If you want the minimum speed, that means you want maximum range for that minimum speed. What angle should you make this ramp to get maximum range for a given velocity? The angle should be 45 degrees. Remember, that gives you maximum range for any given velocity. So if we solve this, we're going to plug in 45 degrees, but we're going to do 2 times it. And we want to get, our range needs to be 30. And I use 9.81 here. You could also use 10. It'll give you a very similar answer. And if you solve it, you'll figure out the minimum speed would be 17.2. That's if the angle is 45. Please realize, if you use a slightly shallower angle, you would have to go faster. Or a steeper angle, you might be able to, you'd have to go probably a little bit faster as well. But yeah, there's a whole bunch of other ones that would still get you across the canyon, but it would require much larger velocities. Talking about air resistance, we've ignored air resistance up to this point in this chapter, but I just want to briefly talk about it a little bit. The actual path, what would happen? As it's traveling this way, the horizontal velocity would not remain constant. Remember, we've always assumed that it actually stays the same at every single point. In reality, with air resistance, it's going to continue to get smaller, which means, as you notice here, it's not moving nearly as far. This is not symmetric anymore. Its maximum height, it doesn't move very quickly over here because the horizontal velocity keeps getting smaller and smaller and smaller as it goes. Start out large here, and it gets smaller and smaller here. And so you'll notice it's no longer symmetric, where it was symmetric around this point up here without air resistance. Because of that, we usually launch things at a slightly shallower angle. Up to this year, this was the record field goal. That's actually just changed recently. But take a look at this particular shot. In this case, we're assuming that they went a little bit shallower to get maximum range because of air resistance. So I'm saying 43 degrees. And it reached a distance of 60.35 meters and hit the goalpost at a height of 3 meters. So it barely made it. But take a look at the math on this one. In this case, what do we know? We know the x position is 60.35. We know the y position is this. We don't know the launch velocity, nor do we know the time. So what do we have in this case? We have simultaneous equations, or a system of equations. We have 2 equations with 2 unknowns, time and initial velocity. You could solve the top equation for either v sub 0 or time, and then plug it into the other one and solve it. Or you can use, I use the TI Nspire just to make my life a little bit easier. and do the system of equations there. And it will tell you, aha, the time and velocity that we won is right here. It also gives a negative answer, but that's not the one we won. So in this case, the kicker actually had to kick the ball at 25 meters per second. That's a little bit over 50 miles per hour. That's an amazing kick to get that kind of range. This is related to your lab. What you're going to do is you can either do this yourself, launch a projectile in the hallway, or just use my pre-done video. There's going to be a whole separate one. And what you're going to do is mark the position of the ball each second as it flies. You need to have a meter stick in the frame to give us a reference. Please watch the video to how to perform this data analysis. When you get your data, you're going to get this. You'll get a beautiful X versus time graph. May not go negative like this one, but you'll get a position versus time. And what I want you to do is actually fit a formula to it. And you might say, whoa, 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 what's going on here? Well, this is 1/2 a, because it's times t squared. And this term here is going to be our initial velocity in the vertical direction. And you'll be able to solve it. But go ahead and take a look at the video that describes how to analyze the data. We got a brain break right here. I'll get you started on this one. In this case, it's a symbol one. In this case, you should recognize this is lipstick. So the star means lip, and the club symbol means stick. And you can work your way through this. These are all two-word answers. That's a headlight right here. So you can figure out what those two mean. The question is what does triangle, solid, circle mean? And you can figure that out by looking at these various things. Oh, got it. I had to think about myself. I'll give the answer if you want to pause the video. In 3, 2, 1. Answer for the one that we're looking for was figurehead. You might say, wait, how does triangle mean figure? Triangle in this case, that's supposed to be a stick figure here in this case, over here. And you had headlight up here. And so figurehead. Makes sense. I want to take projectile motion to the extreme real quick. It turns out, if you throw something, remember it falls in 1 second 5 meters below the point it would have been without gravity. So imagine she's throwing this very quickly horizontally. If she throws it slowly, it's going to fall 5 meters and end up here. If she throws a little bit faster than 1 second, it's going to travel further horizontally while it's falling, and it'll end up at this position here. If she throws even faster, so it travels all this way in 1 second, it's going to end up here. You might notice something. Notice that the Earth is actually curving away here. Is there a magic speed where the ball doesn't hit the ground? And let me kind of work your way through this one. It turns out if you take a laser and set it on the desert, say out in by Palm Springs, find someplace that's open, level a laser perfectly level on the ground, shoot a laser out, and as you walk away from the laser beam, you'll discover that it seems to be going further and further above the ground. What's going on here? It's not that the laser beam isn't going up, it's the fact that the Earth is going down. In fact, by the time you walk roughly 8 kilometers this way, the laser beam will be 5 meters above the ground itself. You might say, oh, wait a second, 5 meters? Wait. Yeah. If you throw a ball from 1 meter above the surface, the ball will still be 1 meter above the surface after 1 second if it's moving at 8,000 meters per second. You're like, wait, I don't get it. Well, if it's going 8,000 meters per second, it's going to cover this 8,000 meters horizontally in 1 second. And during that 1 second, without gravity, be here. But because of gravity, it's going to be just 5 meters down from that. If it started out 1 meter above the ground over here, it's still going to be 1 meter above the ground over here. It's not going to hit the ground. And so now, believe it or not, I can ask you bizarre questions. Roughly how fast is the International Space Station traveling? You're like, wait, I don't know. It's above the Earth's atmosphere. I can't figure that out. Well, remember we talked about this. Gravity is almost exactly the same there as it is at the surface. How fast is the International Space Station moving? 8,000 meters per second. In that 1 second, it travels 8 kilometers horizontally and falls 5 meters. But because the Earth also curves 5 meters for every 8 kilometers you go across, it will follow the curvature of the planet as it falls. And so it never hits the planet. And this International Space Station is in free fall the entire time, which is why the astronauts appear to be weightless. Take a quick look at this one. It's one of my favorite ones. Bugs Bunny is in Queen Isabella's court trying to prove that the Earth is round, throws a baseball, waits a while, la 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 la, eats his carrot, and then waits for it, here it comes, and boom, it just went around the planet. Notice though that if you look at this, none of these cities are in the same. You can't end up in Lima in the southern hemisphere, and Cairo, and then Paris and Brooklyn and Bombay. It'd have to zigzag. But how fast did Bugs Bunny have to throw that baseball to make it around the planet? The answer is 8,000 meters per second. You might say, wait, can we go try this? The answer is no. If you actually attempt to throw a baseball at 8,000 meters per second, what would happen? The air resistance on the planet would literally make it burst into flames a few milliseconds after you threw it. Where can you throw a baseball at that rate and not have it hit the ground? Well, you just need to go above most of the atmosphere. In other words, about 100 kilometers up or 60 miles up. You're above most of the atmosphere. Gravity's still about the same. If you move anything up there about 8,000 meters per second, air resistance isn't going to be too big, and it will literally fall around the planet. Please note that this number is different for different planets and different situations, but for the Earth, it's about 8,000 meters per second for a low Earth orbit. The last idea in this chapter is relative motion. And initially looks incredibly difficult. It's not. A couple of quick things I need to define on this one. We're going to define the origin here as E. And you might say, wait, what's E? E is the Earth frame of reference. In other words, measured relative to the ground. In this case, car A is somewhere up here relative to the origin. Car B is somewhere down here. But here's the question I want to ask. And first of all, a couple of notes on this one. RAE, this is this vector right here, points from the origin to where car A is. And so literally it's the position of car A measured relative to the Earth, measured relative to this origin. And then RB sub E is the position of car B relative to the Earth or the origin. So R sub BE, position of car B as measured by the Earth. And then finally, this is the one we're looking for in this case. If you were a passenger in car B, imagine you're sitting here, where would car A seem to be relative to you? In this case, the position of car A relative to where you're at. So if you were positioned inside this car, where does car A appear to be? Well, mathematically, you can solve this. It turns out, and watch this one real quick, if you want to find the position of car A relative to B, you take A relative to the Earth minus B relative to the Earth. Basically, the E's cancel out, and you get relative A to B. And you're like, whoa, I don't get it. Give me some numbers. All right, let's take a look at some numbers. So, in this previous one, let's say that this car right here is at 10 over horizontally and 10 vertical. So it's 10 this way and 10 this way. Looks relatively close. And let's say that car B is at 9, negative 4. In other words, it's 9 over and then negative 4 down. So its coordinates literally are 9 comma negative 4 relative to the origin. So what does that do? Okay, so we've got our coordinates. How do you solve this thing down here? How do I get the relative position of car A as measured by observer in B? You can literally subtract coordinates. So 10, 10 is the position of A relative to the origin. 9, negative 4 is the position of B relative to the origin, or Earth. And what we have to do is subtract them. You're like, wait, how do we subtract coordinates? Well, what we're going to do is subtract like terms. We're going to subtract x and x, and then y and y. And if you do that, something interesting happens. You'll discover the position of car A as measured by an observer in B is that the passenger we had would say A is 1 further over to the right and 14 up. Now I just want to show you that real quick so you can sort of see it. So from your perspective down here, and I'm going to use purple, it would seem that the car is 1 further over this way and 14 up this way. And that should kind of make sense to you. It's like, oh yeah, our position's negative 4, that's 10, it's 14 up, and it's 1 over. And you're like, okay, that kind of makes sense. So let me put the numbers back on there. It also works for velocity. But velocity is a little bit more interesting. Here it doesn't matter the position of the car, just how fast the car is going in each direction. So let me quick do the same trick. I'm going to break this into its horizontal and vertical components of velocity. Same thing down here, it's vertical and horizontal components of velocity. And now we're going to do the same trick. And just kind of get this in your mind here real quick. To get the velocity of car A as measured or observed by car B, we're going to take the velocity of A relative to the Earth minus the velocity of B relative to the Earth. And by doing that, the Earth kind of gets subtracted out. You're like, do I have to memorize this pattern? Kind of. So in this case, velocity of A relative to the Earth, for this car, its horizontal velocity is negative 15.2, 15.2 point to the left. Its vertical velocity is this. So these are no longer x and y coordinates. These are x and y components of velocity. Likewise, for the other car, its horizontal is positive 9.64, and its vertical is positive 11.5. We're going to subtract like terms, and if you do that, you'll discover the velocity of A as observed by an observer here. The observer in this car would seem the other car seemed to be going very, very rapidly in the negative direction. Why? Yellow car is going this way, blue car is going that way. It would seem to be going negative very rapidly in the horizontal direction, and it would seem to be moving away from you in the vertical. We're going 11.5 in the vertical, it's going 12.9. It's moving away from us, from our perspective, slightly upward at that 1.4 meters per second. You're like, oh, okay, I kind of get it. Well, let's take a few more example problems real quick. A motorboat is traveling at, this one's the classic river problem. AP loves asking this, the river problem or some modification of it. A motorboat can normally travel 6 meters per second east, or it is traveling 6 meters per second east, but it's in a river where there's a current traveling 3.8 meters per second south. What's the resultant velocity of the motorboat relative to the Earth? So in this case, the motorboat's still trying to go straight across the river, but the current is carrying it. So the velocity of the boat in still water is 6 meters per second. But the current is actually taking it downstream at 3.8 meters per second. What's the resultant velocity? Well, it's going to be this vector right here, the sum of those two velocity vectors. Yes, I could do the same thing I did before with relative motion, but we'll just do this one a little bit more simple. That's a right triangle, so how do I find the resultant velocity? We can just do Pythagorean theorem, and you'll discover it's 7.1 meters per second. B. How long is it going to take it to cross the river? Warning. If I give this to you every single time I give it to some of my students, they freak out and go, oh, okay, I need to find theta. then I need to figure out this diagonal distance across the river, and then I can use the 7.1 along with this diagonal distance to figure out the time required. Yes, that would work as long as you don't make any mistakes, but there's a much easier way of doing it. As long as this boat is aimed straight across the river, is the current going to change the amount of time it's going to take to cross the river? The answer is no. The river current is going straight down, and as long as the boat continues, sorry, I'm trying to draw this nicely, continues at 6 meters per second horizontally, the fact that it's moving vertically or southward down the river doesn't affect the time required to cross the river. This is why this is in this chapter. It's very much related to 2D motion. So in other words, it's basically like the horizontal position of a projectile. The horizontal velocity here, which in this case would be the 6 meters per second, is constant even as the boat gets carried downstream. And it just needs to cover 120 meters horizontally. It's going to continue to go that 6 meters per second as it goes downstream. So it's going to take 20 seconds to cross. No matter how large the current is, it's still going to be going at 6 meters per second across this 120 meter long or wide river. It's going to take that many seconds. What distance downstream does the boat reach the opposite shore? Well, here is where the stream's velocity is going to make our difference. That 3.8 meters per second is carrying us downstream for this 20 seconds. Basically, I'm just going to do this. How far does it move in the y direction? Just the vertical velocity times time. There is no acceleration in the vertical, so I can just leave off the 1/2 at squared. So in this case, the horizontal velocity is 3.8 meters per second. The time is 20 seconds from up here. And if you multiply that out, it's going to end up 76 meters downstream. Hopefully that makes some sense. Here are the main formulas for this chapter. Please realize they're actually based on these other ones. Is the range equation critical? Not at all. It's really limited. Which equations does AP give you? It basically gives you these two. And from those, you can come up with the equations we're using for X and Y and everything else. But please realize that these are just derived from these two equations. One's velocity, one's position. And we usually assume that the initial position here is 0. Remember, we make the origin 0, 0. So it's kind of fun. All right. Yeah, again, remember that one only works for level ground. With that, good luck with your homework. You have a relative motion worksheet. It's one of the more challenging ones. And you're going to be analyzing the projectile motion lab. Again, watch that video to help you sort of work your way through it. You'll need one person in your group who has video analysis installed. That is not a free program. It's $4.95 last time I checked, but you'll need to use that.